Welcome back to the class. In the last class we have discussed about the ionic reactions, the introduction to ionic reactions, and how the activated complex theory and the collision state theory can be applied to the ionic reactions. What are the different aspects of ionic reactions, and what are the different type of questions we need to address during study of ionic reactions or kinetics of ionic reactions. In the last class only we have discussed about the calculation of free energy during the ionic reactions, and we come to know that during a ionic reaction actually the ions need to approach each other, and after they will approach each other they will form a structure where the ions participating in the reactions they will be remain intact, and which is called as a activated complex. So actually the thing is that on moving the ions from infinite distance to to a very closer distance which is equivalent to DAB, there is a need of work done, there is a consumption of energy, and that amount of energy we need to calculate, and that was called as free energy. So let us start the ionic reactions. Part 2. This is the continued part of the last class, and we have just gave heading to calculation of free energy. Under that heading we are continuing that when the ions are at a distance, when the ions are at a distance of x, then electrostatic forces between them. You know that from the knowledge of +2 that when two charged particle point charges approach each other in any medium, the electrostatic forces of attraction or repulsion, the magnitude can be given by the expression 1 F is equal to 1 by 4 pi epsilon 0 multiplied by Q1 Q2 by R square. In the similar manner, we will write the expression F is equal to ZAE, charge on particular A ion and charge on D ion. What is E? E is the minimum amount of charges, that is E is equal to 1.6 into 10 to the power minus 19 coulomb. ZB can be positive or negative, positive, negative, depends upon the ion, and divided by epsilon and x square. And here epsilon, what is epsilon? Epsilon is the dielectric constant. As we are talking about the reactions, ionic reactions in a solvent medium, and the solvent have a dielectric, and we know that dielectric have a property of decreasing the electrostatic forces of attraction and also the forces of repulsion between the ions. So obviously the dielectric of the solvent medium will affect the magnitude of the electrostatic forces of attraction or repulsion existing in between the ions. Therefore this term has been arrived and I have used in the expression. What is x? X is actually the distance between the ions. In previous class +2 classes we were using r, now we will use x. X is the distance between the ions. Now the thing is that from which, what is the variation of x is, x varies from x varies from at what distance the ions were present initially. The ions were present initially at an infinite distance, and they at maximum limit they were able to approach to a distance of dab, which is equivalent to the sum of ra plus rb. Now what we need to calculate, we need to calculate the work done. So work done dw is equal to minus of f into ds. ds is the distance, f is the force acting on the ions. So for our f into, we are considering the change in the distance. What is the distance we have taken in terms of x? So what is the change in the distance? That will be dx. Okay. So now what is the magnitude of f is? The magnitude of f is here ZA into ZB. Here E is there, here E is there. That will be E square divided by x square multiplied by dx and 1 by epsilon. We have taken the solvent to be equally distributed or evenly distributed. Therefore the solvent, the value of the dielectric constant of the solvent will be same, will remain same with the negative sign. Now the thing is that why this negative sign is used. Actually the thing is that whenever we are doing some work here, actually we are try to bring the ions closer to each other. So therefore the value of x actually decreases. As the value of x decreases, therefore this is represented by the negative sign. Okay. So dw this is equation number, let us consider this is equation number 3. So what does the negative sign signifies? Here negative sign is used because x decreases by dx amount when the ions move together by a distance dx. So let us consider this is the infinitesimal. The equation number 3 talks about the work done calculated for an infinitesimal change, but for a finite change what we will do, we will add the change calculated during each infinitesimal change and we will take the integration simply. So total work done can be given by integrating each work done of each infinitesimal steps. And what is the variation? The variation is the x. Integration of zb is square by epsilon x square into dx. Now the thing is that what is the variation? What is the variation parameter here? X is the variation parameter here. How it is varying? It is varying from infinite distance to dab distance. Okay. So now we can remove out the constant term. Charges of ions do not change. Obviously does not change, epsilon does not change as the solvent medium is continuous in nature, evenly distributed we have taken. So x will only vary. So taking out the constant term from the integration, we left with the 1 by x square dx. Okay, and now minus of za into zb into e square by epsilon. What will be the value? This will be integration means x to the power n plus 1 by n plus 1. So here x is having power of minus 2, therefore this will be minus 2 plus 1 divided by minus 2 plus 1, and ranging from infinite to dab distance. This will be equal to minus 2 plus 1 is minus 1, minus 1 minus 1 is plus 1. Therefore za into zb multiplied by e square divided by epsilon, and this is equal to x to the power minus 1 and infinite to dab. So 1 by infinite is 0, upper limit minus lower limit, 1 by dab minus 1 by infinite. 1 by infinite is 0 itself, numerically equivalent to 0. This is the total work done a system can do during the approach of the ions. Therefore this is called as electrostatic work done. Electrostatic work done. Okay, and you already know this, the work done, the maximum amount of work done a system can do, that is termed as free energy. So this is nothing but the free energy of electrostatics. This is the electrostatics contribution to free energy. To free energy. And what is the W here? W here is the work done to move two ions from infinite distance to dab distance. So here the expression can be positive and negative, depends upon the nature of the za and zb. So we can write down ki if za zb, the product of za zb is positive, that means either this is positive or that is positive, b is positive, zb is positive, then your product will be positive. But if a z is negative and zb is also negative, then also the product will also be positive, and therefore the nature of w will also be positive in nature. But if any of the term is positive and another term is negative, then obviously the product will give you a negative value, and therefore the nature of w will be negative in nature. That means, what do you mean by this? That means whenever two similar charges are allowed to allowed, or we are trying to bring the two ions having same charges, then the W is positive. And in chemistry, anything which is positive, energy in terms of positive, that means we need to supply energy to the system. That means to bring two ions of same charges, we need to supply large amount of energy. But in a total, I am talking about. But when two ions of opposite charges are brought closer to each other, W is negative. That means as a total, as a whole, some amount of energy will be released from the system and the system will become more stable in nature. Next point. Okay, now we have this work done, we have calculated only for the electrostatic contribution. But actually, in a ionic reactions, there are not only electrostatic contribution are also there, but also some of the non-electrostatic contribution is also there. That means what is happening to the solvent, the rearrangement of the solvent medium. There are different type of non-electrostatic contribution can also take place, and the free energy or the work done calculated for that non-electrostatic processes are said to be as free energy due to the non-electrostatic contribution. Therefore, a term for non-electrostatic free energy will also be there for calculation of the total free energy of activation. Therefore, we can write down there is also non-electrostatic contribution to delta G activation. Therefore, now whatever the work done we have calculated, that is calculated for one ion only. But actually, if we consider, there may be any number of molecules will be there, any number of ions will be there, or 1 mole of ion will be there. So if we say work done for 1 mole of each ion, we get, what is the, simply we will multiply by Na. For one species, that is the value. For Na species, we will multiply by Na by DAB. This is for 1 mole of species, and this is your equation number 5. So this is the value for N number of species, but for one molecule or one species, ionic species, to consider free energy of activation per molecule. If delta G activation is the free energy of activation for N number of molecules or N number of species, for one ionic species it will be given by dividing by N number. And obviously the total give free energy is the sum total of non-electrostatic term, and also it is a sum of electrostatic term also. So now we will use the expression what we have just calculated. This is the ZA into ZB into E square divided by epsilon DAB. Na get cancel out. Na get cancel out. Numerator Na was there, denominator now Na is there. Therefore they get cancel out. And this is the total gives free energy of activation for a single molecule or single ionic species. And as we already know that K, rate constant K, is equal to Boltzmann constant into temperature divided by H. This is nothing but the decomposition frequency, which we have discussed in the activated complex theory, multiplied by the free energy of activation factor n into k. Instead of r, I have written n into k. So now we'll use the expression kt by h into e to the power minus of delta G activation and Es by R into T. Minus ZA ZB E square Na by Na into KT into epsilon dAB. This is the free energy of activation for Na number we have written. Okay. That is, we have utilized the expression. The expression we have just utilized is delta G non-electrostatics plus ZA ZB into E square Na epsilon dAB. This is the expression which we have just used instead of delta G activation. Okay. So now separating out KT by H power delta G activation non-electrostatics R into T to the power N can be cancelled out. Therefore, this is equal to ZB E square by epsilon KT dAB. And N get cancelled out. And therefore, this is the rate constant. This is the KB terms. Boltzmann constant terms. Okay, taking ln on both sides.